When Comet 3 I/Atlas burst into humanity's awareness during the summer months, it immediately electrified the astronomical community, not because it posed any danger, but because it represented something extraordinarily rare, a confirmed visitor from another star system. Interstellar objects are cosmic messengers, fragments of distant planetary systems that have wandered for millions or even billions of years before briefly crossing our own solar neighborhood. Until very recently, such objects were purely theoretical, discussed in models and equations rather than observed directly. The discovery of Comet 3 I/Atlas marked only the third time scientists had ever conclusively identified such an interstellar interloper, and its arrival triggered an urgent scientific response that unfolded at remarkable speed and on an interplanetary scale. The initial detection occurred on July 1st when the Asteroid Terrestrial Impact Last Alert System, or ATLAS, survey telescope in Rio Hurtado, Chile, spotted a fast-moving object that immediately stood out from the countless asteroids and comets routinely cataloged by modern sky surveys. ATLAS is designed primarily to identify near-Earth objects that might pose an impact threat, but its wide-field scanning capabilities make it exceptionally good at catching unusual visitors as well. Almost as soon as the data were analyzed, astronomers realized that this was no ordinary comet. Its velocity, measured at approximately 137,000 miles per hour, was far greater than what would be expected for an object gravitationally bound to the Sun. Even more telling was its trajectory. Instead of following an elliptical orbit like typical comets that loop around the Sun and return again, Comet 3 I/Atlas traced a hyperbolic path, meaning it was passing through once and would never come back. These two characteristics together provided compelling evidence that the object originated beyond the boundaries of our solar system. Once confirmed as interstellar, the comet's importance skyrocketed. Only two such objects had ever been observed before, one I/Oumuamua, discovered in 2017, and Comet 2 I/Borisov, discovered in 2019. Each of those earlier visitors had already challenged astronomers' assumptions. Oumuamua, the first known interstellar object, baffled scientists with its unusual shape, lack of a typical cometary tail, and strange acceleration behavior, sparking debates that extended far beyond astronomy into popular culture. Borisov, by contrast, behaved more like a conventional comet, complete with a visible coma and tail, yet its chemical composition hinted at subtle differences from comets formed around our Sun together. These two objects suggested that while planetary systems elsewhere in the galaxy may form through broadly similar processes, the details can vary in intriguing ways. Comet 3 I/Atlas now entered this exclusive group, offering a third data point and a crucial opportunity to test emerging theories. What made the response to 3 I/Atlas particularly remarkable was how quickly scientists mobilized resources across the solar system. Within just 3 months of its discovery, spacecraft operated by NASA and the European Space Agency that were already stationed at Mars were repurposed to observe the comet as it passed through a favorable viewing geometry. These spacecraft, designed primarily to study Mars and its environment, were never intended to observe interstellar objects, yet their instruments could still provide valuable information about the comet's brightness, composition, and activity. In the coming weeks and months, additional spacecraft on trajectories toward Jupiter were scheduled to join the effort, turning what might otherwise have been a fleeting astronomical curiosity into a coordinated, multi-planet observational campaign. This kind of scientific improvisation reflects both the excitement surrounding interstellar objects and the current limitations of space exploration. At present, humanity does not have the capability to launch a dedicated mission quickly enough to intercept such fast-moving visitors once they are discovered. Designing, funding, building, and launching a spacecraft typically takes many years, while interstellar objects announce themselves only shortly before they pass by and vanish into interstellar space again. As a result, astronomers must make do with whatever assets are already in place. According to Karen Meach, a planetary astronomer at the University of Hawaii who has been deeply involved in the study of these objects, every confirmed interstellar visitor is treated as precious. The moment one is identified, researchers around the world drop their ongoing projects to focus on it, squeezing every possible bit of data from telescopes and spacecraft that can be brought to bear. By repurposing existing missions, scientists effectively gain a bonus experiment, extracting groundbreaking science at little additional cost. Beyond the logistical triumph, the scientific motivations driving this scramble are profound. Interstellar objects are essentially time capsules from other planetary systems. Unlike planets, which are difficult to observe directly around distant stars, these objects physically enter our solar system, allowing astronomers to study them in unprecedented detail. By comparing their properties to those of comets that formed around our own sun, scientists can test whether the processes that shaped our solar system are universal or whether they vary significantly from star to star. Comets in our solar system are thought to be remnants from its early days, preserving ices and dust that record the conditions under which the planets formed. Interstellar comets serve a similar role for other systems, but with the added advantage that they provide direct samples from environments we cannot otherwise access. Early observations of Comet 3I/Atlas suggested that it was actively outgassing as it approached the Sun, producing a coma and tail typical of comets composed of ice and dust. This behavior immediately set it apart from Oumuamua and aligned it more closely with Borisov. Yet detailed measurements were needed to determine exactly what kinds of ices were present and in what proportions. Differences in chemical composition could reveal the temperature and radiation environment of the comet's home system, as well as the processes that led to its ejection into interstellar space. Even similarities would be scientifically valuable, reinforcing the idea that the basic building blocks of planets and comets are distributed widely and form under comparable conditions throughout the galaxy. Chuan Ji, a planetary astronomer affiliated with the University of Maryland and Boston University, emphasized the significance of now having 3 confirmed interstellar visitors to compare. With each new object, patterns begin to emerge, and anomalies become more meaningful. One object might be an oddity, but 3 start to hint at underlying trends. If future discoveries continue this pattern, astronomers may eventually be able to classify interstellar objects into different types, much as they do with asteroids and comets in our own solar system. Comet 3I/Atlas, with its distinct speed, trajectory, and activity, adds another piece to this emerging puzzle, suggesting that interstellar visitors may be more diverse than once imagined. The study of these objects also carries implications that extend far beyond cometary science. Understanding how objects are ejected from planetary systems can inform models of planet formation and migration. Interstellar comets likely originate from the outer regions of their home systems, where gravitational interactions with giant planets can fling smaller bodies into deep space. By estimating how frequently such objects pass through our solar system, scientists can infer how common these processes are elsewhere in the galaxy. The fact that 3 interstellar objects have been detected within just a few years, despite the challenges of spotting them, suggests that the Milky Way may be teeming with wandering debris from countless planetary systems. In this context, Comet 3I/Atlas represents not just a scientific curiosity, but a glimpse into a much larger cosmic story. It reminds us that our solar system is not an isolated island, but part of a dynamic galactic environment where material is constantly exchanged, albeit on vast timescales. Each interstellar visitor carries with it a record of distant stars and long-lost planetary systems, offering a rare opportunity to study them up close. Whether Comet 3I/Atlas turns out to be chemically exotic or surprisingly familiar, its brief passage through our celestial neighborhood enriches our understanding of how planets form and evolve across the galaxy, reinforcing the idea that while our solar system may be unique in its details, it is likely shaped by processes that are universal.